Može. Okay. Ooh, okay. So yeah, we're starting with our next presentation. You know, all of these messages that you exchange in the cloud via the Orange Tessie bot, that's not exactly what Dejan will talk about, but yeah, it has some keywords in there. So hope that you enjoy his talk, rate it, prepare to ask questions, and enjoy.
Thanks. So thanks, guys. Thanks for coming to this session. I'm Dejan. I work. Did we start it? Can you get the slides? Perfect. So my name is Dejan. I'm working for Red Hat in the messaging and IoT engineering team. Year after year, Vox guys gets me here to ramble about the projects we are working on in areas of messaging and IoT. And this year I would like to talk about a scalable messaging platform on top of the Kubernetes called NMAS. So we'll start by taking the step back and talk a little bit about what messaging really is, because it's different things to different people. We'll see some basic techniques needed to scale a messaging platform, and in the end introduce the NMAS project, which is our way of creating a scalable messaging cloud platform. So, you know, messaging has been with us in software engineering for decades, and basically it's a way for applications to communicate with each other. So when we're talking about applications, we can talk about internal components of the distributed system, or we can talk about external system connecting to our application. And in all these cases, depending on the technology you were using, you will probably hear something like that sender or producer are sending some kind of messages to a consumer or a receiver. Usually what we see, and we'll see in this presentation today, that it doesn't have to be like that, but usually this communication is done asynchronously, so that producer and consumer are decoupled. But also there's an element of time decoupling between the producers and consumers, meaning that, you know, messages can be consumed by the consuming applications on their own time, no matter when the message was actually produced. So some of the basic communication patterns that people use in messaging, we all know request response, right? Publish subscribe is when we try to send a single message to multiple consumers. This is usually, you know, used for some kind of notification systems, or, you know, something that's called competing consumers, or usually also known as point-to-point communication is when a producer sending messages to multiple consumers, but we only want that message to be handled by a single consumer at a time. Usually, you know, used to do some work load balances and things like that. Job queues, work queues, all that kind of stuff. Then, you know, when we figure out how we want to, you know, communicate between the systems, then it comes the question of quality of service or delivery guarantees that our messaging infrastructure will offer to the applications. Starting with the most simple one, at most once, in some protocols also called QoS 0, quality of service 0, which means that, you know, we will try to deliver the message, but there are no guarantees that that messages will be delivered between the producers and consumers. So, you know, in terms of failures, in hardware failures, network failures, software failures, there's a potential of messages being lost. And, you know, for a lot of use cases, this is, you know, totally acceptable, and you know, infrastructure to do with kind of traffic is much simpler than, you know, the others. So, you know, for most use cases, so for a lot of use cases, at most once is okay. One, you know, simple example you can have is like having sending telemetry data from a temperature sensor somewhere. If you use reading from the sensor for 5 minutes, it's not the end of the world, right? So, you know, you will get next readings, so you can handle this kind of stuff. For more precious data, so to say, so more valuable data, we can introduce some delivery guarantees. So we can have at least once. which means that the messaging infrastructure will guarantee that messages will be delivered at least once to the consumer, right? In case of different kind of failures, we're all talking here about distributed systems, so failures are, you know, a regular thing. Consumer can receive messages more than once, so we can have duplicate messages, and we need to have that on mind when writing our consuming applications. The last one, exactly once, introduces even more chattiness between the messaging components in the system, trying to make this exactly once delivery of messages between the producers and consumers. And it's mostly controversial one, because, you know, we can maybe guarantee delivery exactly once, but processing of those messages are also questionable. So it's not maybe not worth it going into there. So if you take a look at this, maybe, you know, coming from the Java world or JMS world, you can see that at most ones usually are what's in JMS world called non-persistent messaging, and these two, you know, at least once is called the persistent messaging. So and again, when people talk about messaging and messaging infrastructures, so far, most commonly, you know, we are talking about message brokers, and message brokers and message brokers allows us to do this asynchronous and time decoupling between producing and consuming. So there are two kind of contracts in the system: contract between the producer and the broker. When the producer sends a message, and broker says, okay, yeah, I have this message and I will deliver it later on to the consumer. Then when the consumer comes, the broker sends the message, and then the message gets accepted. This has nothing to do with the delivery guarantees. Even brokered messages can be, you know, QoS 0, because broker can keep this message temporarily only in its memory. So if broker goes down, we lose the messages, or it can safely store the messages on a disk, and then, you know, guarantee that message won't be lost in a transfer. But recently, what we also have is direct messaging. What we focus on mostly in our messaging efforts within Red Hat is the AMQP 1.0 protocol, and that protocol is symmetrical protocol, meaning that we can use broker, or we don't have to use broker. We can connect producers and consumers directly, which you know is even maybe better for some use cases, like request reply kind of thing, when we don't need a brokered thing, you know, between us. But it's even better because we can introduce another messaging component here, and that's a message router. This is implemented inside of the Cupid dispatch router project within Apache Foundation. And the difference between the routing and the brokering is that if you compare these two slides, is you can see that a router never owns the message in this case. It just works very similarly to the network router, but in terms of a messaging protocol on an application level. So it will have its own routing map, know about producers and consumers, you know, dealing with different addresses, and it will simply route the messages and commands between the producers and the consumers. There are also a couple of more features of AMQP 1.0 protocol that allows us to do this in a proper way. So there's a built-in flow control, so that, you know, consumer at every time gives to the router and the producer its credits. It's how much messages it can produce at a simple point. So, you know, producer will only be able to send as much messages as consumers is willing to consume at a certain point. So if you take a look of both approaches, we have a store and forwarding, and we have a direct messaging, and then we can have with both of those two different kind of delivery patterns. So, you know, multicast, or like publish and subscribe and point to point. We have pretty much 4 different kind of addressing semantics that we can support with this. So typical queues and typical topics that people are well known of in the JMS world, and then we have the similar thing, but using only direct messaging between the two. So the basic idea about creating a scalable messaging platform is to do something like this. One of the good things about the message routers is that also you can configure them to create a kind of a network of routers. So in that way, you can also get some kind of more reliability in your system, because the router will try to route the message, on the shortest path. But if something goes wrong, or some of the component fails, we have backup paths through which messages can flow, right? And the thing is that brokers are generally hard to scale. If you take a step back and think a little bit of the brokers, they're basically are very specialized databases for temporarily storing the messages. And as every database, there's a lot of state, there's a lot of context, and it's pretty hard to scale them properly. Routers, on the other hand, are very simple components, and by themselves are much more scalable than brokers. But even there, it's much easier to just add more routers in the router network and configure them properly and provide a great a scalability of that layer. So the idea, the basic idea that these routers configured in a mesh network can be ideal candidate to deal with to be like a gateway into the messaging system, because they can scale to very large number of incoming connections. They can deal easily with very large number of addresses and messages flowing to that system. And then, we can have brokers basically virtualized behind the router network. So we can do different kind of things. We can, easily, elastically scale out and scale down brokers. We can partition queues. We can, shard a single large queue without clients ever, noticing that something like that is happening in the system. Other than that, we can also support different kind of use cases. So for people that only want direct messaging, those messages don't need to go through the broker, so it can all stay in the router network layer. So even further lowering down the load on the broker infrastructure, which is something that we want to do. So the idea behind the messaging platform is to do something like this. So messaging platforms are nothing new. There are a couple of commercial vendors like Amazon or Microsoft and Google providing their offerings. As with everything else today, people don't want to manage their own infrastructure. They want to put a credit card and have everything provisioned for them. And there are a couple of things that are problematic with the commercial offerings. Not problematic, but in terms of being open source and supporting open standard, we thought that there's a room there to do it like that within the messaging. And that's the basic idea between the NMAS project, so which is hosted on GitHub at the moment. The idea is to provide the open source messaging platform built on Kubernetes and OpenShift, but also supporting open messaging protocols like AMQP 1.0 and MQTT. So some basic things, what we want to support here. We want to support here everything that I talked about so far. So both store and forward and direct messaging, both multicast and anycast patterns in any of those things. We want to provide a good scalability and elasticity of the whole system, so that you can easily scale up and down your infrastructure, depending on the current load. We want to support open open protocols, MQP 1.0 and MQTT for the moment. And building a platform, we want to be easily to set up, manage, and monitor your thing. And deployable on-premise, on your own hardware, in the cloud, or in some kind of the hybrid environment. One more important feature of every platform is multi-tenancy. So basically what you want to do is to be able to support multiple accounts in the system. And when I say account, I don't mean only billing accounts and things like that. By tenant in a messaging system, we want to have them having independent address space of its own. So that even within your own organization, you can have multiple teams working on different projects using the same messaging infrastructure, and they both can use the same queue name test. So that's the tenant. So they are both different in terms of the address space they're using. So I want to start talking about all this from the top up. So what we did is provided the OpenShift environment for deploying this kind of infrastructure. And if you are messaging a user, you really are not interested in brokers. You're not interested in the OpenShift consoles and pods and containers running there. You as a messaging user, you want to know the URL where your clients are connecting and your addresses you're going to use and what semantics are those addresses are providing you. So Nmas provides you a kind of a messaging console where you go there and you create your own addresses that you want to use. So you can have queues, you can have direct addresses and topics, and what happens next is that the Nmas will provision the necessary infrastructure for that address to be properly supported. So we are talking about addresses, and we treat addresses in Nmas as a Kubernetes resource. So basically, we can have things like name, of course. Then we have a couple of specifications details of each address, and these two are the most important. So for every address we define is the address store and forward. So does it need a broker to be supported, and is the address multicast or not? So multicast address means that the message will be delivered to all the interested consumers on the single address. So combining these two properties, we can define all the necessary messaging patterns that we want to provide. I'll talk about the flavor a little bit later on. So, as I said, combining store and forward and multicast, we can define all the messaging semantics we want to do. So queues, topics, anycast, and broadcast. So flavor, even if we are not interested that much in how our queue is deployed, they're from the perspective of an application developer, the messaging operator that operates the platform is. So we need to define some way to say, this queue is a queue for my demo projects. I don't need any expensive storage hardware to do that. You can keep those messages in memory. No, never mind. And we can say this other queue, this is a really large queue. It can't be done on a single broker. We need to scale it out on the multiple brokers. So this is where the flavors come in. It gives us a little bit like a flavor of an address that's going to be used. So the messaging operator can go into a system and define a flavor for different kind of addresses. In this case, we can see for this queue, we can define which template will be used, because everything is done with Kubernetes templates. When the queue is created, the brokers with the appropriate template is created, and then we can specify things like how many memory will be assigned to to that running container, which exact image will be used, changing the configuration of the broker if needed, and things like that. And then, the messaging user can choose according to its plan from a couple of existing flavors for the destinations he's creating and addresses he's creating in the system. So just some of the examples of addresses, of flavors for addresses. So you can say, I want queues that will be just in memory. I want persistent queues. I want, you can define scaling, as I said, so this will be hosted on a single broker. Will be hosted on a pool of brokers. Even you can go even further and say, for this queue I need HA, so I need a couple of brokers that I can, survive hardware failures and things like that. So this is all tuned with address flavors. And then we come to this nice picture. So this is how the whole architecture of the system looks in behind. So I'll try to go box by box and try to give you a brief example of how things work. So on the right side we have clients, right? And they connect to the system through the message router layer, as we explained earlier. This is MQP 1.0. For MQTT, we have an additional subsystem here. I'll cover that a little bit later. And then, so the messages that are going to use only direct messaging addresses, this is where all stops. But for queues and topics, we need to deploy a broker or set of brokers to support addresses that are used there. So the messages for the queue will flow through the routing network, be stored on a queue, and then consumed the other way around. The left part of this picture shows the configuration. So this is the messaging thing. So this is where actually we are doing our messaging, sending and receiving messages. The left side is components that are used to configure and deploy and manage the system. So we said that the system is multi-tenant. So this admin box is basically all the components, and those are Kubernetes services and deployments that are per tenant. So each account will have one of the admin things that will manage the infrastructure for them. In this box, there's also a console which is not shown here, the console that I showed you before. On that console you go, you create your address, and that creates basically calls the address controller. Address controller is a component that manages address spaces and a particular address within the address space. So it has an API which is HTTP or AMQP, by which you can control address spaces or addresses basically in that JSON format we saw on the one of the slides earlier. And when we say create a new address, address controller will do the thing. It will configure the routers. It will deploy the brokers if needed in terms of the pods in the Kubernetes, and contact the OpenShift master. The OpenShift master, as I said, those addresses are Kubernetes resources. It can expose changes to those resources, and that's what the config service is listening to. And as we internally also try to use messaging to build this system, it will convert from the Kubernetes kind of API to the AMQP API. It will send messages to the topics, to the addresses that other services can listen on to inside of the system, and react on that and do the things. So router agent basically listens to all the addresses and all the new pods that are coming from the OpenShift and configuring the routing layer, the messaging layer, while the queue scheduler is doing the similar thing with the brokers and configure queues on different available brokers. Topic subscriptions are also a tricky thing to do, because when I say topic subscriptions, we think about topic subscriptions on a certain broker. Those needs to live on a one particular broker. So there needs to be a service that will listen to the addresses that needs topics and configure appropriate brokers accordingly. For the MQTT, as I said, all this system from this point on is based on MQP 1.0. So to support MQTT at the moment, we had to build a couple more components. The MQTT gateway basically do MQTT MQP protocol conversion. So, and that's the easy part. But as I said, most of the protocols are broker oriented, and MQTT is like that. And by being broker oriented, you're basically saying that there's some store, there's some session state that client assumes that is stored on the broker side. So one of the examples in MQTT land is last will and testament service. It's a message you define that will be sent when you disconnect from the service. So we need to keep something like that inside of the system, and that's what this component is used for. So we can now talk a little bit about how we can go and scale things in this kind of environment. So for the router level, I said it's not that hard. Basically, Kubernetes by itself gives us a lot of tools for easily deploying more routers, deploying more brokers of the same configuration, dealing with things like that. So that part is solved by the infrastructure. But we still need to provide some mechanisms for those components to discover themselves in order to work in an appropriate way. So if we start a new router, we want that router not to be standalone. We want it to be configured in a full mesh of routers. So what it will do when it starts, it will connect to the router agent, the component we showed earlier, this one, and ask about all other available routers in the network already. And when it gets that information, it will connect to all of them. And that, by doing this, by scaling up the router pod, we basically added one more router in the whole router network and provided a more scalability in the gateway level of the system. I mentioned multiple times so far that the brokers are more tricky beasts to deal with in terms of scaling. So you can imagine a picture like this, kind of a simplified view of how things work. So clients come to router network, brokers A handles a queue, brokers B handle a topic, and for the queues it's easy because in an environment like this we don't want to we can't order any guarantees, so every broker is for itself. That's okay. But for the broker, for the topics, they need to be connected because topic subscription lives on a single broker, and each of the messages can hit one of those brokers. So we need to have a basically mesh of all brokers that are handling a single topic in order to deliver that every message to each of the subscribers, no matter on which of the brokers they are located. So when we want to add more capacity to a single queue, we can simply start a new broker, and it will connect to the router network. And by using the specific ID of this queue, the routers will know that that's the broker which handles a specific queue, and it will just start to include it into all the traffic, round robin messages between all the brokers. In the topic case, it's a little bit, again, more work because each of the broker needs to find out about all the other available brokers and connect to them as well. Scaling out is also an important feature of any platform, because if we don't need any more, if you don't need that much capacity anymore, we can scale down our infrastructure and save on the costs. What's used at the moment in NMAS is something that's called Kubernetes prehooks. So when you scale down the certain service, there's a prehook that's executed before the containers are being shut down, and we use that at the moment to do our work. And the work in the queue case is simply stop all incoming traffic from the router network and get all the messages from the broker, all the state that's saved on the broker, and push it back into the router network. By pushing it back, the message will be spread around on the other available brokers for that address at the moment. Again, topics are even more complicated use case, because we need to find one other specific broker there and move the subscriber directly there, create a queue, move messages there, and redirect all the subscribers on that particular broker. Monitoring is important part of any messaging platform. So OpenShift and Kubernetes are coming with their own monitoring, but it's all related to monitoring the containers and the pods. As I said, messaging user is basically never interested in that kind of metrics. They want to know about the number of addresses they have, the depth of the queues they're using, and things like that. So NMAS provides that as well. Every of the components use either Prometheus or Jolokia to send its metrics to the system about different messaging metrics, and then it can all be visualized in Grafana, which is a natural way to do things in Kubernetes and OpenShift. There's a lot of things to do. Some of them are in progress, some of them are being finished. What we're basically focusing now is providing more flexibility in authentication and authorization area, and using a key cloak for that, to be able to better integrate with other systems that also want to use NMAS and have their own integration and authentication requirements. We want to provide support for more protocols than AMQP and MQTT, like HTTPS or COAP or something like that. And even what we said here is a scalable messaging. When you use scalable messaging, you lose some of the features that JMS users are accustomed to. So distributed transactions and message ordering, message grouping, people still want that. So we want to provide a way to expose the brokers directly for the people that want to do that, to get them more features and less scalability. So direct broker address space, and provide also other flavors of messaging, and especially support Apache Kafka. So there's a lot of things to do. I hope I'll see you in the community and playing with the project, and ping us about any questions you might have. That's it. Thank you.
So you were very quick. So there's one question in this producer router consumer schema. Is there any persistence guarantee if the router goes down?
There's not, because the router is just an intermediary component here. So the all communication goes directly between the consumer and the producer. So, and how you achieve resilient messaging in that case is to provide, as we talked about, like a mesh network of routers, or redundant routes in the system. So if one router goes down, your messages will be flowing through the other routers in the system. But the router never owns the message, so there's no persistence. That's the whole point of the thing, and that's why it can scale better and provide different kind of messaging patterns.
Again, I need to run.
I can first. So I have two questions. First is, what is the status of the project? I mean, is it production ready or is it in development? Have you, are you as Red Hat supporting it currently?
It's in development at the moment. We had a couple of releases. I'm not sure about exact dates, but you know we are going to build a product based on it very soon.
But not at the moment, right?
At the
Soon,
moment,
but
there's
at the
no product behind it,
yeah.
but yeah,
Okay.
that's the goal.
And second question, what do you mean by supporting Apache Kafka?
We mean
It sounds interesting, but I don't understand what do you mean by that.
What I try to explain today is that you know we have different messaging semantics that we can use. You know, so we can have a traditional broker messaging, we have direct messaging. Kafka also add a little bit different kind of messaging there as well. So what we're going to support is Kafka behind the AMQP protocol. So we will provide and maybe even expose directly Kafka in this kind of system. So
there won't be any Kafka underneath, but
there will be, yeah. But special address space. So if you want direct messaging, use it. If you want Kafka, use this, and then have a same console, same API to configure, manage Kafka as well. Yeah, that's the plan. Thank you.
And I guess the launch impacts like your voting
I'm ready
score.
as
So yeah, I don't know how, but yeah, we'll see. So great, Dejan, and yeah, you want a question? Oh.
By the way, what is the default message broker you're supposed to use?
So what we use, these are components. Yeah, I haven't been clear about it. For the brokers, we use ActiveMQ Artemis. It's the new version of Apache ActiveMQ. And for the router, we use QP Dispatch Router, which is being developed.
And the second question, if I may.
Yeah.
As I understand correct or not, so you haven't built abstraction level when clients will not exactly know which message broker they provide the reliability and...
That's something that most of the clients give you. So you connect over using your client.
You just push message on some address and some consumers receive message from some address.
It's the same as you do today. So is it on your machine or is it somewhere in the cloud? It's just a change of the URL, right?
And for ActiveMQ it makes sense.
Yeah. So we also have a JMS 2.0 client built that uses AMQP underneath. So that you can use in traditional JMS application, you can migrate them to the new client and then go through the AMQP protocol and platform like this. Cheers. So I'll be around the whole day. If anybody wants to chat about messaging or anything, feel free to pull my sleeve.
So okay, that's it then.
Thank you.
Thank
Guys.
you. See you in 1 hour.